this conference on tropical geometry, Berkovich spaces, arithmetic D-modules, and p-adic local systems. And so I'd like to thank very much Andrea and Ambrouche for putting this up. It's certainly been quite a difficult task and to handle such a conference in those complicated times, but I'm sure they did a great job, and we're going to see many very nice talk, I expect. And we start with so Matthias Jonsson from University of Michigan will tell us about K-stability from a non-Archimedean perspective.
All right, thank you. So let me try to share my screen here. Okay, that's disabled. So I'm not allowed to share my screen yet.
Oh. I cannot do it. Andrea or Ambrouche, can you allow Matthias to share his screen?
Otherwise, I can just talk, but it might
yes, just wait a second. Or yeah, spotlight video. Rename putting in. Okay, I don't see where share screen. Multiple permissions can share separately.
Sorry.
Oh,
try to do it, please.
Okay.
Now I think I should be able to.
Yeah, you should be able to do it now. I gave permission. I just okay.
Okay.
Is that good? Is that visible?
Yes.
Yes.
All right. Well, thank you. So I'd like to thank the organizers, Andrea and Ambros, for the opportunity to speak here, to open the honor to open this conference. Of course, it would have been nice to actually be in London, for example, but we'll have to make do with what we have here. So, yeah, so I'll report on some ongoing work with mainly with Sébastien Buxom, who have been kind of doing this for a while, also some other people involved. So it's about K-stability, but from a non-Archimedean perspective through Berkovich spaces. So conference has a slightly eclectic title here, but at least I touch upon one of the words, the Berkovich spaces, pretty solidly, not sure. And maybe indirectly tropical geometry, less so about arithmetic D-modules and p-adic local systems. But anyway, so let me, right, I'll start with, here's the background to the whole story. And it comes from complex differential geometry or Kähler geometry. So I don't expect most people to be experts on this. Not sure if I would count myself on it either, but here's the story. It's something called, it's some work around the Yau, Tian, Donaldson conjecture. So what is this about? So this, at least in the formulation I care about here, it's about a smooth projective complex varieties over complex numbers. So it's X, smooth projective, and L is some ample line bundle of some dimension n greater than equal to 1. And then you're interested in finding kind of transcendental objects. So Kähler metrics in the fixed cohomology class given by L, or the Chern class of L, first Chern class. So this, you think of a closed 1-1 form, Kähler form omega, think of that as a metric, and you want that to have constant scalar curvature. And that leads to a differential equation, which you can write like this, where S bar is a cohomological constant. So you can ask, does these kind of gadgets exist? So I won't say too much about it, very little actually. So, but it's true certainly when n is equal to 1. So then X is just a Riemann surface. And I mean, you essentially have the usual, let's see if I can keep this, the usual thing, right? So for a Riemann surface, either a sphere or torus or something of higher genus. And have like the spherical metric, say the Fubini studio metric or the flat metric or hyperbolic metric. Right. But in the higher dimensions, there are various obstructions and kind of a long story, which I'm not going to do here. But with the YT conjecture for these three people then says that there exists such a metric if and only if the pair XL is what's known as k-stable. I put k-stable within quotation marks because there are kind of various versions of this notion that are kind of closely related, and the devil is a little bit in the details here. But the idea is that in any case, this case, I'll say essentially what this means, but it's in principle a purely algebro-geometric condition, so it doesn't involve any metrics or anything, any transcendental objects. There's been a lot of activity on this in recent years, and what I'll say here is very far from complete. So, but I will say a few main things. So here's the main case, which is somehow both the most interesting, but also the most tractable one. So that's the one X is the Fano manifold. So that's kind of the case of positive curvature in some sense. And when you pick the ample line bundle to be minus the anti-canonical bundle. And this was done by Chen, Donaldson's son, Tian, a few years back. I guess it was published in 2015. So that was really a breakthrough. I should also mention Berman, who kind of did the other direction. Both directions are not trivial, but the most difficult direction is to prove that stability condition implies the existence of a metric. Now there are other proofs in the Fano case. There is another proof, and this is probably also incomplete list. There's another proof by Datar and Sekalidi, which is kind of the same spirit, but with important technical differences. There is a proof by Chen, Sun, and Wang using the Kähler-Ritchie flow. Then I was involved in a proof which will be relevant for what I do here, although I won't really talk too much about it, in joint work with Robert Berman and Sébastien Buxon, using a variational method. And we use, at least we're kind of inspired by non-Archimedean geometry. And just, I mean, we use it, of course, if you really wanted to avoid formulating that way, you probably could. But in any case, that, and we also use some pluripotential theory. Then Li, Tian, and Wang took that up and pushed it a little bit further, and also treated the case when X is possibly a singular variety, Fano variety. In any case, I will come back towards the very end to something about this problem, but for the most part, I'll kind of focus on the non-Archimedean interpretation of what k-stability means. So that's, okay. All right, so here's the objects that were used to define k-stability. I guess this definition or version of it is really due to Donaldson, but there's a lot of preceding work as well. So the idea is to look at one parameter degenerations of the pair XL. Some degenerations that are also C star or GM equivariant. So you start with a polarized variety, and you can think over C, but what I'll talk about today is, let's work over an algebraically closed field, K, and later on I will need it to be of characteristic 0, but actually not in the beginning actually, but let's just fix that from the beginning. So what is a test configuration? So basically it's a test configuration for X and one for L. So you put X in a one-dimensional family over A1. It's a flat projective morphism. And then you equip this script X with a line bundle. So L is line bundle. The script L is semi-ample. Maybe I should say relatively semi-ample. Then I have an action on everything, which lifts the action on A1, and everything outside the central fiber is just isomorphic to the product with A1. So essentially I have kind of X here, and I kind of just put it in a one-dimensional family. So here's, but over the central fiber, over kind of the origin here, I have something. So here's A1, and here's X. Oops, sorry. This is the central fiber, and I have an action of GM here. And then of course I have the line bundle as well, or the Q line bundle and so on. Okay, so in this situation, you can define a bunch of invariants. And really the invariants originally were defined by looking at the action of GM on the central fiber. I also have sections of the line bundle on the central fiber. But it was later, let me not write it that way. So I'm going to use a formula which is due to Odaka and Wang. So this is going to be df here. This is the Donaldson-Futaki invariant. And it's defined slightly sloppily like this. So A and B are some constants. The main point I want to say is that it's in terms of some intersection numbers. So first you take L to the power n plus 1, except that I write L bar. And what I do is I can also add a fiber over infinity in a kind of a trivial way. And then I get L bar X bar. So I take the intersection product of that, n plus 1 times. And then I also use the intersection with L n times with this relative canonical bundle. And I put some constants A and B, which are just cohomological. So let me not worry about those. Then there's a bunch of other invariants. There's something which we call the J functional, and it acts as some kind of norm of XL. So what are kind of the simplest example of a test configuration is when I just have the product with A1, that will have norm 0. And essentially the norm tells you whether something is close to this one or not. And then you're saying that the pair is K semi-stable if the Donaldson-Futaki invariant is always non-negative. And then there's a whole slew of different versions, stronger versions of this when you say when it's 0, or can you say that it's quantitatively bigger than 0. So that's the later one, the other one that I'm going to use, which is saying that it's uniformly K-stable if you have, it's kind of bounded below by some non-negative quantity. Maybe I should also say, hold on, I'm not going to swipe this under the rug, that I'm implicitly assuming that maybe that X doesn't, or XL doesn't have a lot of automorphism. Otherwise, you should probably, definition still makes sense, but they're not going to be valid. The uniform K-stability is not a good definition there. All right, so anyway, so those definitions have been around, but at least conjecturally, and I think, I'm not exactly sure what the status of proof is for this, but it's generally believed that it's not, that it may not be enough to, always be enough to just look at test configurations, or at least certainly for technical reasons, it's good to look at more general objects. And so I'm going to look at kind of two different ways. The first one was already, it's this one here, which already suggested by, I think already by Donaldson, certainly worked out by Sekalidi. This is about using filtrations of the section ring. So the section ring of XL is the sum of sections, space of sections of multiples of L. So that's on the one hand. And the other one is to look at a certain class of functions on the Berkovich analytification of X. So I'm going to call these, they're kind of Plurius Harmonic, I mean, at least relative to L. And the goal is to explain these and the relation between these from a non-Archimedean point of view. Okay. And as one always say, please do stop me if there are questions. So I'll start with Plurius harmonic functions. I mean, of course, this is quite condensed. So I'll try to emphasize what I feel are the most important things here. So the notion of Plurius harmonic function, I mean, that really originally comes from complex analysis. So it's a kind of a CN version of a convex function. I mean, harmonic function is a generalization of a convex function, say in one variable. And the higher dimensional version, if you want, being of a convex function is rather a Plurius harmonic function, or at least it's not one. So here we want a non-Archimedean version of this. So you want to work with the Berkovich analytification of X. So in this conference, I'm not going to define that, except that for what I'm doing, it's actually convenient to view the elements kind of, to use additive terminology. That's maybe not what everybody likes, but it's kind of works pretty well if you want to keep the analogy with a complex situation. So in some sense, the elements here, I want to view them as semi-valuations. So kind of taking where semi means that it can take value plus infinity. Right. So now the idea is that if I have a test configuration XL, this induces a function on Xn. So I'm not going to define this. It's not super hard, but it's just leads kind of a digression. So instead of doing that, since we're at the non-Archimedean conference, let me just say that this works the same way as a model metric of Ln, right? So usually when you work over a non-trivial, so here I'm using the trivial absolute value on K. So a model of X, there is really only one model, which just is X itself. So that's not very interesting. So test configurations play the role of models in this theory. And then usually a model of a line bundle gives rise to some metric, model metric on the identification of that line bundle. And here it kind of works the same way. And these are it's a continuous function. These are quite nice. And you want to think of that as a kind of a piecewise linear function in some sense. So now you can look, so the set of such functions, let's see, maybe I should write, I made a mistake here. So when I write for the set of such functions with, I want to say L is actually semi-ample. I want some positivity condition here. Maybe, I'm not sure if maybe I did assume that already before. Right. So you can talk about test configurations, which are not semi-ample, but anyway. So you can think of them in two ways. On the one hand, this space H is like kind of convex or QPL functions, piecewise linear functions Rn. On the other hand, you can also view them as smooth positive Hermitian metrics on LH, where L is, this is like the, if I work over the complex numbers, of course, I can also use the usual analytification, the Archimedean analytification. There you can have the whole theory about smooth Hermitian metrics and so on. And this kind of plays that role. And the same terminology, the same notation is typically used in that theory as well. Right. So now that's the space associated to test configurations. And now I want some more general spaces. So the kind of success, there's a whole slew of spaces here. I'm going to define E1 on the next page. But first of all, I'm going to look at PSH, that's decreasing limits of functions in H. So all of these, maybe a thing to have in mind is that if I have piecewise linear convex functions, if I take kind of decreasing limits of these, well, I can get some more general convex functions. Of course, it's not a perfect analogy because these Plurius harmonic functions can have the minus infinity locus. It's much more closer to what happens in Cn. But anyway, you define it like that, and I'm excluding the function constantly equal to minus infinity. Then I have the bounded functions, that's E infinity, bounded PSH functions. And then I have functions that I kind of approximate from above, from below as well. So that's kind of, I take piecewise. And again, on Rn, in R, you don't really see the difference of this, but there's some kind of subtle difference of approximating from above and below, which I probably won't be able to get into. Anyway, so these are some classes that you can cook up from these test configurations. So I should mention, I mean, this is maybe our definition, but certainly this doesn't appear in a vacuum. So there's a lot of work. I mean, you can view these functions in the class PSH as some kind of semi-positive metrics on Ln. Or at least if they're continuous. They've been studied a lot by people like Shou Zhang, Gubler, Chambarlois. I've done myself with Buxom and Favre, and then also Chambarlois-Dicot, Gubler and Kühnemann, and many others. There's not a complete list. But the point is, this is for the trivial absolute value of K, which I'm working on here. All right, so now I need, among these classes, among these PSH functions, an interesting space is something I call E1. So these are functions of finite energy. So maybe I should. So there you can define the Monge-Ampère. You can define a function on space H of test configurations by, I should put a bar here, some intersection of theoretic invariant like this, which turns out to be very natural from various points of view. And it has some, it's monotone and also kind of equivariant with respect to addition. So you can naturally extend it to the set of all PSH functions just by approximation from above. And then you say that the space of functions of finite energy is the one of finite energy. The E is strictly bigger than, it's not minus infinity. So this is exactly an analog of something that's been studied a lot in complex geometry by, I guess it really goes back to Segrel in the case of Tian, but then in the more in a more geometric situation, especially by Gedge and Zariai. I also mentioned Darvas, but there are also many others. For what I'm going to do, there is something I would, well, I'm not sweeping it under the rug because I'm mentioning it here, but I won't. There's one technical assumption which we need at some point to make things work. And that's something that's a non-trivial result in the complex case, and there's something called continuity of envelopes. So this is if I take a continuous function, so think about it, on R, this would be maybe a function like this. And then I want the convex envelope. So I take the supremum of all convex functions below it. So in the, maybe it would be something like this in the case of a convex function on R. Oops. And the point is that this is going to be continuous. And that's a statement which is true. It's not a trivial fact, but it's true if X is smooth and K has characteristic 0. So we prove this using some multiplier ideals. There is a version under some conditional result also when in characteristic P, but you have to assume resolution of singularities. Anyway, I'm just gonna kind of implicitly use this from time to time. Not always, but so now on this space, you can define a metric, just a distance. I call this the Darvash metric because Darvash didn't work in the non-Archimedean setting, but in the complex setting. And they didn't define it this way, but it's a formula which is useful. So if I take the distance between two functions phi and psi, I take the energy, I use these Monchampère energies, and I subtract the energy of kind of the minimum. So what I mean here, phi wedge psi is just the minimum of phi and psi. Of course, the minimum of the two convex functions is not convex. So I take the convex envelope, or this PSH envelope, and then I subtract this. And now the first theorem, which is really just an analog of a result by Darvash in the complex case, is that this space E1, D1 is a complete metric space. And it's going to contain this space H as a dense subset. That's actually not the hard part. The hard part of the difficulty here is actually proving the triangle inequality, which we actually use. We do it using kind of what comes next. And the completeness actually turns out that's really where we use this continuity of envelopes assumption. We're going to use it later on as well, but okay. So that was one thing. Now, you have the other point of view. Instead of working on Xn, you could also work kind of with, I guess there are probably some, can call this quantization or something, but I'm not going to use enough words already. So I'm going to study the section ring of L or XL. So that's it's the ring of sections. So it's this sections of multiples of L, and I'm going to call Rm as the H is 0, X. It's the sections of ML. So I'm going to look at, so that's a ring. I mean, it's a finitely generated K algebra. It's a graded ring. You have the grading there. I'm going to consider norms on R. So when I say norm here, I mean that it's a norm in the sense of, the usual non-Archimedean sense. So it's a non-Archimedean vector space norm, but also it's submultiplicative. And again, this is of course not standard, but convenient here. I guess that Briand and Titz also use the same term convention to use, instead of using norms in the usual sense, you do that kind of additively. It will just be more convenient for what I do here. So chi is minus log of a norm. So norm 0 corresponds now to plus infinity instead. And then norms are in bijection with filtrations. So I just say that the filtration of R here is when chi is greater than or equal to lambda. And I will restrict to graded norms, which just means, I mean, this is a graded ring, so I just norms that respect the grading, or equivalently, there is an action of k star on the non-zero elements of k on R, and I want this to be invariant on the action. So that just means that I have this equation here. So I'm really just given, I just need my norm is determined by its restrictions to Rn. Now the fact is any test configuration, so that's what we wanted to have, want to generalize test configurations. And you can, any test configurations induces a norm, or if you want a filtration, and this is, well, this doesn't determine it completely, but just say that the elements of norm at least lambda will be exactly the sections of M script L here. At least maybe here I'm assuming actually that script L is a really line bundle rather than the Q line bundle, but let's not worry about that. And such a norm is of especially nice type. It's a finite type. So it's really, once I know what the norm is doing on the first few RMs, then it's completely determined on the rest. And the converse is also true. And all of this is kind of up, it's a little bit inconvenient to write it, but it's up to replacing L by a multiple. Okay. So this is the idea that you generalize now, the test configuration induces a norm, and now I can generalize the situation by looking at more general norms, not just, say, finitely generated ones. And in fact, I can look at the space of all norms. So the space of just non-Archimedean norms on a finite dimensional vector space is, of course, a very interesting object itself. We kind of use that, but I will not kind of do the whole theory here. So instead, I would just want to, so what we want to do is want to look at like some kind of limit of these guys or compatible systems. So for each RM, I have a norm, and I have this sub-multiplicativity condition as well. I also want kind of a boundedness condition. This is not part of the definition. I mean, we are going to use this. So I'm going to say that the restriction onto Rm, it's always bounded below and above by some constant times m, right? Where for a fixed C, not depending on m. Right, so then one way to study, I mean, here it's just a trivially valued, it's a norm on a finite dimensional vector space of a trivially valued field. So it's a fairly simple situation. And you can associate a lot of data to this. But in particular, I can look at it, just the values that this norm takes additively, just finitely many values, or then also plus infinity. I'm going to order these with some kind of multiplicity. So there are nm, the dimension of Rm, these values, and then you can do various things with them. And the only thing I want to define here is I take the average value for each m, and then you can prove that the limit of this exists as m goes to infinity. You can prove many more things than this. You can prove that there's some kind of convergence to a measure, a limit measure of these things, spectral measure. But this goes back, well, maybe this version was known before, but a good place to look at this is the paper by Buxbaum and Chen, which I think is from 2010. I could be wrong about this. And now you can define, that's the volume. Now you can define a metric on, or it's rather a semi-distance on the space of norms by similar kind of construction. I mean, I'm not sure if you really want to define it this way, but it's a convenient to write the definition like this. So I take the volume of a norm plus the volume of the next norm, and then I subtract 2 times the volume of the, here is the minimum of 2 norms. And in this case, I don't need to do any convex envelope or anything like this. The minimum of 2 norms in my additive convention is again a norm. So the way this, so somehow I really go between chi and here is the minimum and chi prime. So the distance between chi and chi prime is really the same as the sum of the distances between these two. So you shouldn't think of this as a there are no unique geodesics in this space. There are geodesics, but well, we're not going to talk about that, but they're not unique. Okay, so you can check that. Well, so first of all, you define, or you can define it in this way, that two norms are, you want to just say essentially that two norms are the same if they, you don't want to say that they are equal necessarily. They could be, you could take any given norm and change it on the first few RMs if you do it carefully without changing it on the rest. And in that kind of operation, it's kind of trivial. You don't want to say that that produces a new norm. And you can make this precise by saying that two norms are asymptotically equivalent if this semi-distance is 0. So this semi-distance does satisfy the triangle inequality, which I think the way I wrote it here is not going to be trivial to verify, but you can do it some other way. And then if you quotient out by asymptotic equivalence, you can show that D1, I mean, that also has to be verified, but you can prove that D1 kind of descends to really a distance on that space. So that's really a metric space. Now this one is not complete, but we'll talk about that in a minute. Okay. Right, so now I have two objects. I have these started with the Plurius harmonic functions. I mean, when I say Plurius harmonic, it's a respect to a line bundle. You don't expect otherwise, strictly speaking, to have Plurius harmonic function on a compact space. There should just be constants. So it's kind of more like, usually in complex geometry, you talk about omega Plurius harmonic functions relative to a Kähler form, omega. Anyway, so you have those, and then you have the graded norms. So those are both generalizations of test configurations. And now it's kind of natural to compare the two constructions. And there are various things to say, so I want to formulate it in this particular way. So I want to define a Fubini-Studi operator, because this is somewhat analog to how you construct like the Fubini-Studi metric just on projective space, or more generally if I have a very ample line bundle. And there is, of course, a non-Archimedean version of this, the Fubini-Studi metric on, say, 001 on Pn, and it's kind of related to that. That's why we call it this way. So it's something that takes a graded norm, n, chi, to a function which is going to be a Plurius harmonic function, but it's going to be an approximation from below of nicer functions. So, let's see. So I do this. So fs chi, it's a limit as m goes to infinity of some scaled versions of fsm chi. So these guys, let me see. These guys actually lie in the nicer space H. So these are, and then this limit is essentially an increasing limits. It's at least, I mean, it's the kind of subadditivity. So it's increasing with respect to divisibility. And it's pointwise, at least it's equal to the sup here. So I take limits on each FSM. Well, I can write it with this formula here, which is maybe not so illuminating, but it really is, well, I can also write this as it's a max over some I. So if I have, right, so if I have a basis S1 up to SNM, so if this is like an orthonormal basis for RM, then this is just a max of, so then I have chi of SI, so this is some lambda I, or lambda, yeah, lambda I, and then minus V of SI. So this is just a finite max. So this is going to be a nice, you can see, well, it follows that you have to do a little work that to show that this actually is something coming from the test configuration. It's not so hard. So I'm kind of approximating, I get some kind of function. This is my Fs of chi, and it's kind of approximated by guys from below. Right. All right, so that gives a map from norms to functions. So the theorem here, and I should say that we're assuming this continuity of envelopes for this theorem to be true, so it's conditional on that, but it's true at least if X is smooth. We do expect it to be true more generally, at least when X is unibranch or something, for example, normal. Right, so the first statement is that this map is surjective. So you really get all kind of PSH functions that can be approximated well from below. So it's surjective, and also we can say that kind of what the fibers are. And in fact, so the fibers consist of norms that are asymptotically equivalent. So this equivalence relation here is asymptotically equivalent in the previous sense. And moreover, we also had these metrics or distances on the two spaces, on the equivalence classes of graded norms and the metric on PSH functions of finite energy. So here this is just injective, it's not surjective anymore because it's E1, which is a bigger space, but this is actually an isometry. So the distances are preserved and the image is dense as well. So somehow people had been looking, sort of as I mentioned, the idea of using norms or filtrations, I guess, to generalize test configurations had appeared quite a bit earlier. But in some sense, we're showing that up to taking some suitable equivalence relation on on these filtrations, you can put it into kind of a nicer space from certain points of view, at least with respect to this metric point of view, that E1 is this bigger space that also is complete. So it's a metric completion of that space. Right, so there's a bunch of things that go into the proof. But one of the main things is a relation. When I do this Fubini-Studi metric, there's one invariant that works well. So on the one hand, I have this Monge-Ampere energy. This is the E, which is on nice functions is defined. If you're given by test configuration, it's an intersection number. Otherwise, it's defined by limits. And on the right-hand side, you have this volume. And you can show that you have, well, I mean, so this Fubini-Studi metric and this has this nice property here. And this uses, well, some earlier work. I mean, you approximate chi by finitely generated norms. So that kind of approximation procedure can be handled using the technique of Ogunko bodies, for example. And then in the case when you have a nicer graded norm, you could use some earlier work of myself and Hisamoto and then Buxom. Okay, so that's essentially what I wanted to say. That's about how to compare two generalizations of the notion of test configuration. But now I wanted to, for the remaining time, go back to the kind of situation we started with, which is, I mean, the motivation from all this was K-stability. So even though not everybody here is an expert on that, I still wanted to say something about where that is going as well, where we use this for. Unfortunately, if I want to define everything, it's a lot of notation, which if you haven't seen it before, I think is very hard to digest. So I will just hide a lot of things, which might have other disadvantages, but let's do this. So the idea is that K-stability, if you remember, that's the way I formulated it before. It was kind of a conditions of various functionals on the space of test configurations. Well, now the space of test configurations, that's, I can identify, well, up to some equivalence, but which I'm sweeping under the rug, but it's essentially the space H of kind of nice pluriharmonic functions. But I can also imagine having more things to test. So I can have a functional on this bigger space, E1, where it has some other nice properties. And it turns out that somehow our philosophy, this is much more based on that you should work with this space, at least for certain aspects. It's kind of natural. And so there are a whole bunch of functionals. And again, I'm not really going to define them. The main point is that they're all modeled on existing functionals that are used in Kähler geometry. So these are typically defined using, I mean, there's also the Monge-Ampere, there's a Monge-Ampere operator, which is the differential operator, and you kind of play around with all kinds of combinations of those. So there are, roughly speaking, two types of functionals. There are some that I could call energy functionals. There's something I call E, I, and J. So there are quite a few of them. And just to make things worse, within the literature, people use conflicting notations for these two, which is not completely ideal. But anyway, I'm using our notations. Then there are also some entropy functionals, H and L, and maybe some others. So the energy functionals, so they involve, as I said, some essentially coming from what in the complex case is, it's a mixed Monge-Ampere measure. So it's essentially like a second order, but a non-linear second order differential operator. I mean, the Monge-Ampere, the usual Monge-Ampere measure of a Plurius harmonic function is that you take all the second derivatives, or the Levy form, and then you take the determinant of that. It's kind of the analog of the real Monge-Ampere operator, which is the determinant of the Hessian. And then you can do mixed versions of these, and you can do all kinds of things. And this E of V, I already defined this before, but it has this property that, right. So it's essentially an integral of this phi itself, and I'm integrating with respect to some kind of mixed thing. So here I have a certain number of copies. I guess I have J copies here, and I have N minus J copies of 0. So that's one example. And then you do combinations of these. And then it turns out that the way this Monge-Ampere in the non-Archimedean setting, the way the Monge-Ampere operators are defined is ultimately through intersection numbers and approximation. So when phi comes from test configuration, this energy is an intersection number like the formula that appeared before. And these kind of energy functionals, they're nice in the way, on the nice type of convergence you have on this space is usually, I mean, you can have uniform convergence, that's of course good, but you don't, that's too strong usually. So instead, the second best is to have decreasing limits. That's kind of how PSH, the whole space, was defined, as some kind of decreasing limits of elements of H. That's good. And then you can also do increasing limits, which turns out to be quite a bit more subtle, but that's also good. But arbitrary limits are, these functionals are not very well behaved. But they are continuous under monotone limits. All right, so then you also have entropy functionals. So maybe, yeah. So you can also do, there's another integral which takes into account the log discrepancy function. So that's a function used very much in algebraic geometry, at least when defined on divisorial valuations. And then you can extend this to general valuations, or the whole xn, in a kind of canonical way. So this is when x is smooth, or at least has some mild singularity, say KLT singularity. And this is related to Temkin's work on the kind of metric on the canonical bundle, or more generally. So this entropy functional here, h of phi, is I integrate the Monge-Ampere measure against this ax. Problem is this ax is not, it's only a lower semi-continuous function. So it's quite delicate. So this one is not continuous under monotone limits. And in fact, we conjecture based on what's true in the complex case, this conjecture is valid here. So then it's saying that you can at least approximate from above any element of E1 by nicer ones and having convergence of this H along these. Right. So that's enter. And then I mentioned before that there was this Mabuchi functional on test configurations which defined K-stability. And here you can define this now more generally. So I should say that this is for phi and E1. I can define the Mabuchi energy as something like this, where F is a suitable energy functional. Okay. All right, so that's a whole lot of definitions. So it's a fair question to say, are they useful, right? I mean, you can always have natural generalizations if you kind of like the non-Archimedean point of view, which I would hope that many do here. But are they actually useful, I think? And I would say yes, and just as an example, a recent example is by Chi Li. So he gave actually a sufficient stability condition for the existence of constant scalar curvature Kähler metrics. So this was, I think, quite a breakthrough. I mean, it uses a lot of other results, but here it's the statement. So let's assume X is smooth, complex, and you assume that you have some bound below, some uniform bound below on the Mabuchi functional on the whole space E1. Then there exists a constant scalar curvature metric in that cohomology class. So in some sense, it's a non-Archimedean analytic condition, but I mean, ultimately it doesn't use the transcendental structure. So it doesn't use the Archimedean norm or anything. So it's still a very nice, I mean, I think it's the first really good criterion in this direction. And well, maybe I won't say too much of the proof because I'm over time here, more or less, but I mean, it builds upon a lot of things. So there is a connection, maybe I'll say something. There is a connection, at least, how you go between Archimedean and non-Archimedean. And this is about, you work on a space E1, which is the Archimedean E1. Inside there, you look at geodesic rays, and somehow these geodesic rays you need to look at are associated to elements of the non-Archimedean E1. And you can kind of transfer information between the two that way. Then there is kind of a completely different aspect of the story is to, once I have some kind of variational information, you want to show that you actually have a constant scalar curvature metric. And that's uses some deep PDE's results together with some further results of Darvish and Rubinstein. But I want to just end by mentioning that, in fact, you could even go the other way around. So here it's a sufficient condition, but you can also, this is actually a necessary condition if this entropy regularization conjecture, which I said before, is a kind of a purely non-Archimedean result. If that happened to be true, which I wouldn't say I'm dead sure about it, but it's plausible, then in fact you would have the other direction by, well, also building on some other work, but slightly easier work in this case by myself and Hisamoto and Buxon. But yeah, I think I'll stop here. So thank you.
Okay, thank you very much for the talk.